So here's another thing that we know. That is, if we run value iteration, we get a series of value functions, say, vt. If we compare the value function we have at some time step t to the same value function that we have one time step later, vt plus 1, that if it basically has stopped changing, if the change, the amount of change from t to t plus 1 is less than epsilon for all states in the MDP, then the largest difference between the optimal value function and the value function that we get, sorry for this, but by taking that value function, taking the greedy policy with respect to that value function, and taking the value function of that greedy policy, is small, right? So we're going to be doing almost optimal from all states. And the smallness here ends up being 2 times that epsilon times gamma divided by 1 minus gamma.
Oh, yeah, sure. That's intuitively obvious.
Well, maybe not intuitively obvious, but the Singh and Yi proof of this is not so complicated, not so different from the stuff that we've been doing. And you get the 1 over 1 minus gamma because this little bit of epsilon that we could be off could get magnified over every single step as we think about this into the future. That's why we get a 1 minus gamma in the denominator. And then, 2 epsilon, because I don't know which side of the epsilon we're on, times gamma, because it doesn't take place right away. It's 1 step from now. So it does kind of make sense. But the real important upshot of this is the notion that if you can get a good enough approximation of the value function, then you're going to have a good enough, then you can at least put a bound on how far off you are in terms of following the resulting policy from how far that's going to be from optimal. And furthermore, we don't even need to know how close we are to V star. All we need for this result to hold is we look at 2 consecutive iterations of value iteration, right? Which that we have. We're running value iteration. We know what it was a step ago. We know what it is now. And so we can compute this epsilon, and that gives us a bound on what if we just stop now and follow that policy. So that's a really useful thing. Otherwise, knowing that value iteration converges in the limit is not super duper helpful because you're never going to get to the limit. And knowing that value iteration eventually is optimal, even if finite, is still not that helpful because you don't know when that takes place. So what this is telling us is we can actually test on our own when is a decent time to stop.
So that's cool. So here's something I just noticed. If I look at both your 1 and 2, I noticed that they both would encourage you to pick small gammas. Right?
Yes, it is certainly the case that if gamma is really tiny, like gamma is 0, then this bound stays small, this bound stays small. It's all good. The closer gamma gets to 1, the more things are problematic. But what do you infer from that?
Well, mainly, why is that? Well, that's because gamma really tells you what your horizon is. And so the smaller gamma is, the sort of further into the future you don't look. That makes sense. And so that makes sense then, right? That if I'm not really worried about the future, then it doesn't take much for me to be doing what appears to be optimal.
Yes, that's right. Right. It's easy to optimize over a very short horizon. And the horizon, the effective horizon is always something like 1 over 1 minus gamma. That's kind of how far into the future do rewards actually matter.
Right.
And so, right. So gamma closer to 1 is really looking ahead a lot further. And that's why it's a harder problem to do. It's harder to get things exactly right.
So then why in practice don't we always set gamma to be really, really small?
Yeah, that's where I thought you were going to go. So it's a good question. I mean, one of the things that happens if you set gamma to be something very close to 0 is the agent who's acting in the world acts very myopically, very like short-term thinking. So, I feel like eating now instead of finishing recording this lecture. So, I might as well just do that. Right? So you get short-sightedness.
I am eating now.
Well, that's good for you. I am not eating now. I would like to eat now, but I won't because I'm sufficiently farsighted to know that just getting something yummy to eat right now is going to interfere with my ability to finish this course because our, wonderful and talented video editor eventually is going to stop processing this stuff, and then we're hosed. So yes, smaller gamma means easier problem, but more short-sighted behavior. Closer to 1 gamma is looking ahead more into the distance, but can make the computations more difficult.
Okay, so it's basically what these 2 results are saying is that there's a trade-off between horizon and sort of feasibility of solving a problem in a reasonable amount of time.
Yeah, that's a good way to say it.